I would like Lang to give a short introduction, and then maybe we can take over, because I can see that Phil is not present. So Lang, would you like to just give a quick intro?
Of course, yes, I'd like to give a very short introduction. I'm very pleased to introduce Dr. Isd3. Don't laugh. let me start properly. I would like to introduce Isd and her group from the University of Pisa. Isd has worked on the in vitro dosimetry modeling, and Isd and her team, Hermes and Pietro here, have done great work in trying to package the model that they've been working with me in work package 6 of PATROL into a user-friendly software. And the purpose of today's meeting is to demonstrate how this software works and how useful it is for experimentalists like myself and all of you. So on this point, I would like to pass the button back to Isd, and she would then, without further ado, load the software and demonstrate it to the audience. Okay, is that all right?
Yeah, great. Yes, thank you very much, Lang. So I'm just going to share my screen just to give you a brief outline of what we're going to be doing today. So most of it is going to be hands-on use of the DosiGUI tool that I hope you've all downloaded and have running on your computers, because we're actually going to go through that step by step. So we'll just I'll just give you a very brief introduction to the problem of nanodosimetry and the two models that we're going to be that we've leveraged our DosiGUI on, and then I'll hand you over to Hermes, who will introduce some of the theory a little bit more in detail behind the DosiGUI. And then Pietro is going to show you how to use it, so how to put numbers in and how to get useful data out. We'll show you a couple of examples as we go along, and then at the end of this session, we can discuss some of the problems you might have, and also some of the improvements one might want to include in this tool. So hopefully it'll be very interactive, and if you do need to say something, ask questions, please feel free to do so. Don't feel as if you're interrupting a prepared talk, because it's supposed to be very, very informal and informative. But if you have problems with the software and the installation, then we suggest that you just go into the breakout room where we've already got people who may be able to help you. And if they can't help you, then certainly Hermes or Pietro can leave this room and go in there and give you a hand. So the problem that we're trying to address here is the problem of accurate assessment, accurate identification of the so-called effective dose that cells receive in a cell culture well. So you know that nanomaterials inside liquids, generally when they're placed on top of a culture well or mixed inside the medium, they'll interact with each other. They'll sediment very slowly towards the bottom of the well. And as they do so, they might dissolve, they might move up or down due to Brownian motion. They might also aggregate and agglomerate and therefore move at different speeds if they're bigger or smaller. And all this impacts on how many nanoparticles the cells at the bottom of the well actually see as a function of time and as a function of how high the well is, so how much liquid the nanoparticles have to descend through. So it's not just a question of if I give a dose of 100 micrograms or 100 milligrams of per ml of nanoparticles, that's what the cell's going to see. It's not like that at all, because the cells see different amounts of nanoparticles according to the way in which these particles descend down to the cells. And it also depends on the way in which the cells then might take up these materials or might even not take up these materials. So what we call the nominal dose, that is what you give when you prepare your sample, with respect to the effective dose, that is what the cells actually see, is quite different. And it depends on time, it depends on the characteristics of the nanoparticles, it depends on the characteristics of the cells, and obviously it depends on the characteristics of the culture medium. And all this means that we have to, in order to have accurate hazard and risk assessment, we really do need to know what the effective dose is that our cells are actually seeing, and that helps us to extrapolate our data to the in vivo situation, and it helps us to then properly characterize their safety. So that is the reason why accurate assessment is so important, and is the reason why you need a mathematical tool to be able to do it, because the processes that the nanoparticles undergo are quite complex and depend on a number of things. So the geometry of the system, the characteristics of the nanomaterial, and the characteristics of the cells. So we developed this graphical user interface that hopefully you've all downloaded and have been able to see at least the way it works, at least for the first instance. And we'll take you through that slowly. So what I'll do now is I will hand over to Hermes, and Hermes will give you an introduction to the way in which DosiGUI is structured and what the most important input parameters that we need are for the system. So I'll share the screen that Hermes will present. Okay, over to you, Hermes.
Okay, thank you very much, Professor. And so, good afternoon, everyone. And first of all, let me briefly introduce myself. My name is Hermes Botte. I am a PhD student at the Research Center Enrico Piaggio of the University of Pisa in Professor Alualia's research group. And today, with the help of Professor Alualia and Pietro Vadaggini, who is a master's student carrying out his thesis in our research group, we will show you DosiGUI and how it can be exploited for improving the accuracy of the estimation of effective dose delivered to cell cultures. So first of all, we will have this brief theoretical introduction to what DosiGUI is and how it can be correctly exploited for to this purpose. And then we will hold an hands-on session during which all of you will be invited to run some example simulations and thus learn how to use DosiGUI following our guide with the share screen. So the first question is, why, please, can you go to the next slide? The first question is why focusing on in silico models in the field of nanodosimetry? As introduced by Professor Alualia before, some technical issues are strongly limiting the capability of experimentally measuring the effective dose in vitro, since it can significantly differ from the nominal one. And for this reason, the great majority of in vitro dosimetry studies nowadays refer to the nominally administered doses as constant quantities over time and over space. In this context, in silico modeling could represent a valuable support. And in particular, two models have established during recent years for in silico nanodosimetry, which are the DG model and the Isd3 model, which are able to reliably simulate the dynamics of nanoparticles suspended in an aqueous media. So go to the next slide, please. In this light, in this perspective, and with the aim of encouraging and possibly widespreading the utilization of in silico models in the field of nanotoxicology, which actually, despite of their predictive potential, are almost unexploited, since they, first of all, require the full installation of a licensed computing environment, which is MATLAB, and which also requires the user to have a basic programming knowledge for editing their source code to manage the input and output datasets. So, to enlarging their utilization and facilitating their utilization, we developed DosiGUI. DosiGUI basically is a graphical user interface embedding the two mentioned in silico models for nanodosimetry, the DG and the Isd3 model, and enabling to easily run such in silico models. DosiGUI is implemented as a standalone desktop application, which means that no additional software are requested for running simulation, to be installed for running simulations within DosiGUI. And moreover, DosiGUI enables to homogenize the input datasets of both the Isd3 and the DG models, so that a unique input file containing all the parameters you need to describe the experimental setup in exam is suitable for running simulations with both models, and thus also facilitating the comparison between effective dose predictions obtained from one model or from the other, with the aim of identifying which is the most suitable one for replicating in silico a specific exposure scenario. Go to the next slide, please. Leveraging on the use of DosiGUI, we also proposed a novel integrated pipeline for accurately estimating the dose effectively delivered to cell cultures in vitro. And thus, DosiGUI just represents an integral part of this broader approach. In particular, our approach starts with an exhaustive characterization of both intrinsic and extrinsic parameters of the experimental setup. In particular, physicochemical properties of the nanoparticle of interest, which we want to simulate the dynamics, should be characterized in detail, as well as the extrinsic parameters typical of the experimental setup. Both of them have a major impact on determining the effective dose delivered to the cell culture, and some of them are known a priori, such as the height of the suspension column or the time you want to expose the cells to nanoparticles. But some other could be unknown a priori. For example, the stickiness, the adsorption potential of the bottom boundary could be unknown, and thus you will need to identify this parameter. To this purpose, as we will see at the end of the workshop in the presentation by Professor Ahluwalia, you can exploit the same predictions by DosiGUI for identifying the stickiness of the bottom boundary for a specific cell phenotype of the cell culture. Once the input dataset is complete and you have a detailed characterization of all the needed parameters, it can be fed to DosiGUI for running simulations. But before this, you need to verify that DosiGUI predictions are reliable, and thus you can do it by fitting DosiGUI predictions on properly acquired experimental data. Once, if successfully validated for a specific nanoparticle, DosiGUI predictions can then be extended, as we can see in the figure, in the graph on the top right. These predictions can be extended to any other exposure scenario involving the validated nanoparticle, and then related to their corresponding biological effects induced by the exposure to such nanoparticles to the specific dose determined with DosiGUI, for building dose response curve as accurate as possible. So we will see how we validated DosiGUI predictions for 3 commonly used engineered nanoparticles, and how we identified the empirical constants which describe the absorption kinetics of such engineered nanoparticles onto a specific cell phenotype. But before this, let's have a practical session on the utilization of DosiGUI. And so I'm going to leave the floor to Pietro, who is going to first give you a brief overview about the interface of DosiGUI, so you can navigate the interface with Pietro and see the most important button you can use. And then we will have some example of simulations to learn how to predict effective dose with DosiGUI. Thank you.
Okay, thank you, Hermes, and good afternoon, everybody. Now I'm going to share my screen to let you see how DosiGUI works.
You to put in the chat whether you've actually successfully managed to install the GUI. So just so we can see the numbers.
Are you okay?
If you've managed, that would be great. Yeah, so just
are you able to see my screen with DosiGUI?
Yes, I can see.
Okay.
Okay, I see lots of yeses, which is great. Okay.
Okay, now I'm going to show you how DosiGUI works with a practical example. As you can see, this is the first window that opens up as soon as launch the DosiGUI. There is a brief description of the 2 models that were introduced by Professor Ahluwalia and Hermes, and a little button to get some info on and our contacts. You can see the last update of the GUI and our contacts, our emails. So now I'm going to start Isd3 model to give you a first introduction on the organization of the interface. But as we will see, the organization is exactly the same for both DG and Isd3. So now, as you can see, we have a left side of the DosiGUI with a series of tabs. These tabs allows the user to modify all the input parameters requested for running the simulation. On the right side, we have the post-processing tool that allows us to plot all the output variables that we can get from the model. The very first menu that we have, called the experimental configuration, allows us to load inside DosiGUI an input dataset in the format of a .mat file. But by default, we have loaded into DosiGUI the material, the experimental configuration with the material that was used by the model's authors to validate the model. If we click on load from file, a new window opens up. And as you can see, we can load inside the DosiGUI an input dataset in the format of a .mat file, that is the MATLAB dataset format. And we can load, for example, we are working with the Isd3, we can load the Isd3 input file. We made some input dataset available for you to test DosiGUI. In Isd3 model, we can also load a DG simulation, so a DG input dataset. DosiGUI will then proceed to adjust all the DG input variables to be able to run an Isd3 simulation with those parameters. Moreover, if we jump for a moment to the Start tab, we see that we can name the output file that will be saved both as a .mat file and an Excel file. This file will contain all the output parameters that of the model, of the simulation. But we can also name an input dataset that is saved as a .mat file and that can be then loaded back inside the GUI to run another simulation with the same parameters that we just use, or the user can modify the parameters and run a similar simulation. So going back to the main tab, we see that we have all the input parameters regarding the most important variables, so the nanoparticle configuration and experimental conditions. In the advanced tab, we have the particle diameter distribution settings that must be known from previous material characterization. And for Isd3 model, we have also an agglomeration model. But the user must keep in mind that this model is nanomaterial specific. Moreover, we have the stickiness knob. As introduced by Hermes, particularly important for us was the stickiness identification. So we decided to implement inside DosiGUI the possibility to have different levels of bottom stickiness through this discrete knob that allows the user to select between 3 different levels of bottom stickiness or a completely reflective or sticky bottom. Based on our experiment, on the result of our experiments, we think that these 3 levels of stickiness, or the possibility to have a reflective or a total sticky bottom, we think that should cover all the range to simulate the experimental conditions. Where a completely sticky bottom means that everything that reaches the cell surface is instantaneously taken up by the cells, and a reflective bottom means that the nanoparticles are not interacting with the cells at all. If the user doesn't want to go inside the advanced tab, can also decide to simply disable this checkbox to run a reflective simulation. In the third tab, we have the dissolution model that is specific of the Isd3 model and is nanomaterial specific. So we should not enable the dissolution model if you are not sure about the dissolution kinetics. If we try to load the default settings that actually have the dissolution model, we can simply disable unticking this checkbox. In the other tab, we have, is very important, must always be checked, because we have the resolutions for the simulation. We have both the spatial resolution and the temporal resolution. The resolutions are very important because they heavily affect the time requested to run a simulation, and also the quality of the results. So the user must always try to find a good trade-off between the results quality and the time, the computational time. Now I'm going to show you also the DG interface. As you can see, the organization is exactly the same. Obviously, the model requires different input parameters, but we organized the DosiGUI in the same way. So we have all our tabs. We have the same stickiness discrete knob that works exactly as we saw on Isd3. And we also have a dissolution model in DG. But these dissolution models works differently than the one we saw on Isd3. We have 3 types of dissolution model. One that doesn't allow further dissolution after initial dissolution that can be decided by the user. We can enable a constant, a linear dissolution rate, or we can specify the times and the fraction of the to linearly interpolate. To have a linearly interpolated dissolution model. Here we can define all the parameters for all these dissolution models. And particularly important, we have, as we can see, we have the same resolution that we saw on Isd3. I mean, the height of the simulation element in millimeters and the time step in minutes. Particularly important for the DG model is the spatial resolution, because it heavily affects the quality of the results. We saw that with height of the simulation element of 0.005 millimeters, there is a good trade-off between the quality of the results and the computational time. Anyway, the user must be very careful when changing the order of magnitude of this resolution, depending on the computational power of the laptop, obviously. And in DG model, we find other resolution, in the output tab. These resolution that are always spatial resolution and temporal resolution are referring only to the writing of the output files. So they doesn't affect the computational time required to solve the model, but affect the time that DosiGUI requires to write the output results once the simulation is completed. If we want to save time, we can check this checkbox so that DosiGUI only writes the output, the bottom compartment output in the Excel file that we can name here, just as we saw on Isd3. And obviously on the right, we have our post-processing tool. We can plot a variety of output variables. For this demonstration, I'm loading one of the input dataset we made available for download, a simulation of 72 hours with high stickiness. We can change the name of the output files. And as soon as we start the simulation, a progress bar appears that give us an idea of the time remaining for the simulation. Another thing that happens as soon as we launch a simulation is that DosiGUI creates a log file, a text file named log file, in the same folder where you have to put your input dataset and where DosiGUI will save all the output files. This log file works like a report of all the computations made by DosiGUI and is extremely helpful in case of error. The user can at any time open the log file and so that we can check if everything is okay. And if you are unsure where you have to put your input dataset and where DosiGUI will automatically save the output files, you can for Mac OS user, this folder is always this folder, the main user folder. And for Windows operating system, you have to put your input dataset if you're launching DosiGUI from a desktop shortcut in the desktop. Otherwise, DosiGUI is not able to load the input dataset. While we're waiting, if Hermes, you want to add something, I don't know.
Thank you, Pietro. I think it's been a great overview of DosiGUI. I think that all the participants can try to do what Pietro has done just now. So try to start a simulation with DG model. I don't know if it could be needed to see again how to start the simulation, or if you were able to run to launch the simulation. We are just now writing the output data, I can see. Yes. So we may go a little bit slower.
Yes, unfortunately, with the Zoom screen sharing, DosiGUI is my laptop is a bit slower than usual. But
we can go a bit
we are writing. It shouldn't take much longer. Okay. Okay. Now, as the progress bar tells us, the computation is finished, and in fact, we have on the right we have a plot. We are seeing the effective dose as percentage of nominal. For other output variables, we can also change the x-axis and the media height or the simulation time we want to plot. We always have to press the make plot button. So if we want to save a plot, we have to press the make plot button, and then we can name the plot, for example, effective ggplot effective dose. Now, just pressing this button, save.fig and save.png file, DosiGUI will automatically save 2 files for the user, always in the same folder where we have our input. Files. As we can see, we have the .png, that is just a photo format that can be opened on all operating system, and the .fig file of the same plot that is displayed on the GUI. The .fig file is a figure file for MATLAB that is very useful to run further post-processing. And as you can see, DosiGUI also saved all the output files in the same folder. Now, this file that we just created can be loaded back inside the DG model, or also loaded inside Isd3 with the load DG simulation. When you are loading a file inside DosiGUI, you must always keep in mind that DosiGUI accepts all .mat files. So if you try to load a file that is not suitable for the model, you will get an error. And if you get an error, you will hear a sound effect, usually on your computer, and you will find the error on the log file. And if you are unsure on the folder that you have to save the file, another confirmation is the first folder that DosiGUI shows you when you try to load a file. It's the folder where you actually have to put the file. So if you're not sure, just try to load the file. And I think that's all. And for example, now I just got an error because I didn't actually load a file inside DosiGUI, even if I said load from file. So if I open the log file now, I will find an error in using the load using the load function. This is an example of how the log file can be useful when running simulation. I can also start a DG simulation, Hermes, an Isd3 simulation, I think, if you have the time.
Well, wait for a moment, Pietro. There is a question.
Okay.
The question is by Mary, and she said, is there a database where effective densities of nanoparticles are listed? For instance, those of JRC benchmark particles. I can try to briefly answer this question. Then I think maybe Professor Alwaya or Ilaria can answer better than me. I think yes. For example, for our evaluation that we will see in the last presentation of the day, we used all nanoparticles from JRC benchmark, and basically we can refer to those data sets, to those databases for the physicochemical properties of nanoparticles to feed to DosiGUI for starting simulations. As I said before, the physicochemical characterization of the nanoparticles, as well as the knowledge of all the design parameters of your experimental setup are a crucial point for obtaining consistent results from DosiGUI. As Pietro showed, you have in this first panel, which is called main panel in both the models, you have those which are the most important experimental parameters to set. We can say that advanced and dissolution parameters could be left by default when loading your file, and you do not have measure impact on the simulation. But the parameters which are present in the main panel, and obviously the resolution, temporal and spatial resolution, are absolutely crucial.
Yeah, Ilaria, would you like to add to that? Because I think that these data are available, but you have to be very specific about the media that you use and the amount of FBS. It has to be identical to that used in the JRC or reference protocols. Can you add to that, Ilaria?
Yeah, hi, good afternoon all. I'm Ilaria Zanoni. I take care of the validation part, experimental part, to validate those models. And yeah, regarding the effective density, we have to take care about also the media that you use. So regarding this one, we used some data that were already available within the project regarding this kind of situations. So we use GRC benchmark nanoparticles to check and validate the model. We use titanium, cerium oxide, and barium sulfate. But sure, this value can change and are dependent on the media used. So if you would like to be more specific and you would like to replace and use this model, you have to have this information. So far, we are on the project. We have some of those data available, and depending on the media that you use. I hope that I answered to your question, Marie. Yeah, absolutely. I agree with Siva Kumar. Yeah, you can use the volume simplification method. That is another way to have information about the agglomeration and so the effective density. You can use AUSI or this method, the volume simplification method. And the model is able to run both So you can have one over another.
Yes.
The other thing is, if you don't have the data on a file, you can directly put the numbers inside the software. So if you know the density and the viscosity and the particle diameters, those are numbers you can punch into each of the rows.
Yes, basically you can create your own input file when simulating for the first time a specific configuration. So Pietro has just changed the option to new material. And when you select new material, as said by Professor Alwalia, you can manually insert, manually fill the blanks and insert your parameters you characterize for your setup. So when you start the simulation for this specific configuration for the first time, as we saw before, DosiGUI generates a corresponding input file, a .m file. And so if you then want to repeat that simulation or use the same data set for the other in silico model within DosiGUI, or you only want to edit one parameter, keeping constant the others, you can reload these parameters by using the load from file option in this pop-up menu. And so if you have started a simulation with those parameters, you have the corresponding input file, and you can load it using load from file.
If you want, I can start an Isd3 simulation.
Yes, we can also see there is another question, maybe.
Okay.
Can DosiGUI be used to determine the dosimetry of buoyant nanomaterials such as PP nanoplastics in the top compartment of inverted cell culture, as has been previously demonstrated with DG by C.Y. Watson? I would say yes, but we just need to think about how to input the parameters. So we need to think about that. It's an inverted cell culture, so the cells are on the top, the particles are on the bottom. But that's a special case that we need to work on, Hugo. And another question that we're often asked is, can DosiGUI, so I mean, be used to model carbon nanotubes? So, I mean, DosiGUI is just a graphical interface which integrates two well-known, well-established models, and maybe of the two, the DG model is the more well-established. And if you're interested, Hermes can certainly give you an overview of the two models, how they work. That is the DG and the Isd3, which are incorporated inside DosiGUI. So the two published models incorporated in the GUI, so that users can easily and flexibly apply them to their experiments. So going back to my statement, can they be used for carbon nanotubes? The answer is no, because these two models really work well for particles that are almost spherical, or anyway have a shape that is almost round. So they might be cubical, they might be rhomboids, but they cannot be long and thin or stringy. They have to be fairly rounded, even though the edges may be a little bit ragged. So that's an important distinction to make there. It's useful for nanoparticles with a kind of nearly spherical shape.
Okay. So I was saying we can load an input dataset to start an Isd3 simulation. This is just 24-hour simulation, because on average, an Isd3 simulation takes more time than an ADG simulation. In fact, in in Isd3 we have the possibility to split the computation on more processor. So there is this option that you can change based on your laptop on the number of processors you have available. And as you can see on Isd3 model, the progress bar also indicates us the time step we are currently working on.
I
May
hope,
take some time. So Hermes, if you want to add something or if there are other questions, please.
yes, I hope all of you is being able to start and run the simulation with the Isd3 model. If you have some issues, some technical issues, you can switch on breakout room where we can try to provide some support, technical support for the usage of DosiGUI.
Yes, I wanted to add that if you want just to test DosiGUI, you can simply load one of the input dataset we made available for download and just press start. There is nothing to modify if you want just to test the application.
So someone has joined the breakout room. So Pietro, I'm switching to the breakout room and.
Okay. And in any moment, if you want to check the status of the simulation, you can open the log file. For example, for Isd3, we have a summary of the computation. As you can see, we are at the 1 hour time step. And this log file works as a summary. If you want to update the log file, we have to close it and reopen. So we can see if the simulation, for example, now we are at the 2 hours time step. If we open log file once again, we see that the 1 hour time step is completed and the simulation is now working on at 2 hours. Professor, I don't know if you want to go back to the presentation that I can share my screen later, maybe, because the simulation is taking more time than I thought it would.
Oh yeah, okay.
Okay, so I'm stop the sharing.
So I've just got to figure out how to do this. So while the software is running and working on the Isd3 model, I'm just going to explain to you how the model can be validated, just in case you are using a new setup or a new material. It might be important to actually try and figure out or try and ascertain that the model does actually correctly predict how many nanoparticles are in a given point of your well in time. So as I explained to you, and as Hermes also explained, when nanoparticles are placed in a cell culture system, the materials, don't know why, will sediment at different rates. They may agglomerate during this process. They may also dissolve during this process. So they will change their size during time. And so you saw that video. I can go back again and just, you can see that the smaller ones will move faster, the larger ones will move a little bit slower. So if you run yourself, if you go and test your toxic or cell response at very short times, you may have fewer nanoparticles interacting with the cells. If you test your toxic effects at very long times, you may have a larger number of cells. So it's very time and also dimension dependent. So it depends on the height of your cell culture well. So how do we know that the model is correctly predicting the number of particles in a given plane of your well at a given time? Well, you need to actually experimentally validate this for different materials and for different experimental setups. And the other question that is very important is, how does the effective dose, so how does the actual amount of nanomaterial interacting with your cells, how does that change with the way that the cells might interact with the material? So you might have cells that don't absorb the nanoparticles. There might be some inhibition processes which doesn't allow the particles to enter into and go through the cell membrane. Or there might be some cell types that are particularly easy for the particles to penetrate. And so we distinguished these two extreme types of behavior of cells as cells with which are not sticky, and so the cells tend not to absorb onto, the particles tend not to absorb onto the cells, or cells which are very sticky, and as soon as a particle lands on the cell membrane, it's internalized almost immediately. And this very much changes the effective dose of that the cells see, because if the cells are reflective, if they don't absorb very well, if the nanoparticles don't absorb very well, then the effective dose is obviously much smaller. So we've introduced a stickiness index into the models. It was already there, but it was very kind of, in both models, in both the DG and Isd3, it's very difficult to estimate and introduce a stickiness level. So what we did was we tried to actually measure the stickiness for different experimental situations. And so in order to validate the models in terms of the amount of nanomaterial as a function of time and as a function of space, and as a function of the stickiness of the bottom surface, what we did was, together with Ilaria's group, Anna Costa's group, we actually went and measured the amount of nanoparticles as a function of time in the middle of a well as the particles deposited. So we actually took samples from a well as the particles were, after the particles had been introduced into the well, and we went to measure the amount using ICP, plasma emission spectroscopy. And we then fitted our model results to the actual data. So this is one of the results that we've presented in the paper. We sent you the link. This is just the worst case model that we had. So this is using parameters that we knew wouldn't fit. And you can see that even in the worst case, the measured data quite well match the predicted data. Whereas if we actually improve the sticky bottom conditions, so we move that dial that Pietro showed you towards more stickiness, then we get much better fitting of the data. So that means that the stickiness parameter is actually very, very important. And it's particularly important when we're looking at the interaction between cells and nanoparticles. And you can see that even in the worst case, the fitting parameter, so the R squared, is actually not too bad. So usually an R squared of 0.9 is considered quite decent in for statistical significance. So even in the worst case, we didn't have bad significance. And as we improved the stickiness parameter, this R squared number got closer to 1. So we know that we need to increase the stickiness index of our particular experimental setup. We then went to do exactly the same thing in, or a similar thing, in the presence of a real cell monolayer. So we placed the same nanomaterials in the same liquid medium, so with the same amount of FPS, in the presence of a HepG2 cell monolayer. And then what we did was, at different exposure times, we actually scraped the cells off the bottom of the well, and we went and measured how much nanomaterial was present inside the cells. So we detached the cells, scraped them off, and we went to measure using plasma emission spectroscopy the amount of nanomaterial absorbed into the cells over time. And what we saw there was that using DosiGUI, you can change your stickiness parameters using that dial. And the more we increase the stickiness parameter, the better the data fitted. And in particular, this best stickiness parameter was actually different for the 3 nanomaterials that we used in our experiments. So we used NM105, NM212, and NM220. And interestingly, the most sticky nanoparticle, or the one that had the best interaction with HepG2, was the barium sulfate nanoparticle. So for that, we needed to move the stickiness index dial right up to a very, very high, almost absolute stickiness level. Whereas titanium dioxide and cerium dioxide had a kind of medium stickiness level. None of the materials were reflective, so they all absorbed either very well or fairly well onto the HepG2 cells. And we obtained very, very similar results for both the DG and the Isd3 model. And that's one way of really fine-tuning the experiment and the DosiGUI parameters in order to obtain a much better estimation of the effective dose. So that's some of the validation experiments that we did, and that one could also do in-house if one has access to plasma emission spectroscopy or other quantitative methods. So I'll go back to Pietro now, because I think it should have finished the simulation.
Yes, the simulation is completed. One moment, I'm sharing my screen. Okay, the simulation is completed. We have our effective dose plot expressed as a fraction of nominal. And as you can see, it makes sense since we're running a total stickiness simulation. And we can also check the log file to see if we got any error. The simulation ran smoothly, and we can see we have the confirmation that the simulation is completed and the CPU time required to run this specific simulation. And just like before, we can save the plot and everything will be in the same folder. This was just an example. Keep in mind that this simulation we made available for download doesn't have the best resolutions, because we wanted to be able to run them in without taking so much time from the workshop. So if you try to get better results, keep in mind that you have to improve the resolutions of this input data set. And I think that I show you everything that I wanted. So if you have any question on the GUI, on the installation, if you want to share your screen to, if you got some strange error, please don't hesitate.
Okay, so we're actually at the point where I think we've gone through the demonstration. So what we need to do now is just have a quick question and answer session. So I think really the aim now is for you to start using the system and figuring out, what your problems may be, whether you have any queries. So just for this introductory part and showing you how the system works and how you might be able to use it and exploit it for better estimating the effective dose in your experiments. I'll just thank you all for your attention, even though we haven't finished. I'll just share our emails with you. Obviously, I want to thank the whole of the PATROLS consortium who provided us with all the data that we inputted for the simulations, for Lang for his encouragement, Shireen as well. And we've created a help email address, in case you don't remember mine or Mrs. or Pietro's, dosigui.unip@gmail.com. So if you want to ask us any questions, if you want to suggest any improvements or anything that you might like to go into with in more depth, feel free to send us an email here. So we'll pass on to the questions now. So
yes, I see there is already a question.
Okay.
Can you get out numerical data as well as the figures? Yes, maybe I wasn't very clear. As soon as you, can I share my screen, Professor?
Sure. Stop sharing.
Maybe I wasn't very clear, but as soon as a simulation is completed, you get the two output files that contains the same data. This is for MATLAB. This is just an Excel file that has all the results. These are the input parameters of the simulation, and these are all the results. And if you want to get the data from the plot, then you must go to this file to find the data, or you can use the .fig file, open it on MATLAB, and then extrapolate the data. But everything is saved in these two files, both for DG and the Isd3 model.
Yeah, just bear in mind, Pietro, that most people may not be familiar with MATLAB, so it'll be in Excel. The Excel file has all the numbers that you need.
Yes, all the numbers, and it's exactly the same number that you will find in the MATLAB file. As you can see, we have all the results versus time. This is for Isd3. Okay.
Which model to choose? Now, okay, so I think that the most consolidated model and the one that's also faster, in terms of its computational time, is the DG model. The Isd3 model is very, very specific to silver. So it's very specific to a soluble nanomaterial, and you need to input all the solubility constants. So we found that with the 3 nanomaterials that we used, the the DG was the best, whereas for silver, AG NM300, the Isd3 gave the best results.
Yes, I wanted to add for the question I answered before, that also for DG model, you get all the results from this in the Excel file, but you have to untick this option. Otherwise, you will get an Excel file like this, where you have only the bottom output written. So if you want all the values versus time, you have to untick this checkbox.
That means you'll get all the values of the amount of nanomaterial as a function of time and as a function of height in your well.
Exactly. And as Professor said, the G model is on average faster. But if you want to get better quality results, you have to go down with this number, at least 0.005 millimeters. And this number evenly affects the computational times.
Yeah, that number tells you into how many elements you divide your space. So, you know, 0.005 millimeters is like a fifth of a micron. 1, 2, 3, 5 micron.
5 micron, yes. And that will be the height of the simulation element. So yes. And then you can also run a first DG simulation, then load the DG input that you used on DG on Isd3, run a second Isd3 simulation with exactly the same data, and then you can compare the results. If you don't exactly know which model to use, if you're not sure on which model to use.
Okay, I don't know if there are any more questions. Can you give me which model to choose? Is 0.005 the maximum resolution? That's something that...
No, it's not the max resolution, but is the resolution that we find out as a good trade-off between computational time and the quality of the results. Obviously, depends on the workstation, if you can actually go at lower resolutions.
Yes, obviously it also depends on which is the application for which you need the predictions, basically. I mean that also a little bit slower resolution. So I mean bigger space step, it can be suitable for your application if you do not need something particular refined in terms of spatial resolution.
So what I would advise is to try with worst resolution for the first simulation, and then try to go down with the resolutions after that.
Yes.
Yep,
Okay.
Shireen has noticed that there is a box stating the total time of simulation. Do you advise changing this? At the moment, it's set at 24 hours.
It depends on which is the it depends on which is the exposure time you want to simulate. So basically, I think 24-hour was an example Pietro
Yes,
used.
we actually did a 72-hour simulation on DG because it's faster, and a 24-hour simulation on Isd3.
Yes.
Yes, that's right, Beza. It's the experimental time, not the calculation time.
Yes,
So,
right.
Yes.
yeah.
It is right.
Don't worry, it's a bit faster than the experiment.
Yes.
Oh, okay. Yeah, the stickiness was best for a given nanoparticle. Could you briefly comment on how to predict it? Well, in our hands, the kind of a good stickiness level is a medium stickiness, but we did see that barium sulfate was more sticky, so it was almost maximally sticky. That is a question that we really think is important to address within the nanomaterial community. So we think that with our experience, we think that it's important also to have a database of stickiness of nanoparticles and a given cell type, because I think it changes with cell type. So I think it'd be very interesting to not just characterize the nanoparticle in itself, but also its interaction with a particular cell type. That's something that we're working on at the moment with Anna Costa's group. So for the moment, I would suggest that for common nanomaterials, a medium stickiness is probably the best. There's certainly, we didn't come across reflective surfaces at all, even in the presence of an uncoated well. There was a certain amount of stickiness.
Yes.
But I think that's a question that the community needs to work on. Okay, that's a question for Ilaria.
Yes.
Hi. Well, yeah, we evaluated using DLS. So basically, we were more focused on the total amount of nanoparticles found at the middle age of the experiment. That was part of the experimental validation. But we also performed the DLS measurement to check the different and possible change in the aggregation and agglomeration of nanoparticles. But we just performed this one so far.
So the protein corona thickness for us is then the difference between the nanoparticle diameter and the effective diameter. Okay. In the meantime, Shireen or Lang, would you just like to say a few closing words? We're waiting for another couple of questions, and let me remind you again that if you do want to message us, if you need any help while you're using the system, you're more than welcome to write to us, and that'll help us improve the GUI and ensure that it gets wide use amongst the nanomaterial community, because I think it's fairly important, and everybody knows that effective dose with respect to nominal dose is a much more accurate way of representing and estimating hazard and toxicity. So do feel free to message us when you start to actually use the software, if as I hope you all will.
Thank you so
I'd
much.
like to. Oh.
Sorry, let me introduce you like in the Austria. So first I have to thank Artie, and I think the final word, the closing word, I think it will be wonderful for Sharon to express her view on this, being the coordinator. Okay, over to you, Sharon.
Sorry for interrupting you there, Lang. Yeah, I just wanted to say a thank you really to Artie and Pietro and Emma for this really useful workshop. So from my perspective, I'm obviously very much involved in patrols, given that I'm the coordinator, but I'm an experimentalist. And so I really found this tool very useful just to help us try and understand what we're dealing with when we put our particles into our solutions. I'm certainly by no means a MATLAB expert at all. So I would just like to thank you for today's workshop, because whilst I've had a little look at the DosiGUI prior to the workshop, I must be honest, having the additional insight and the step-by-step through is actually really helpful to make sense of how to use it and what to do. So I would like to say thanks very much to you all for that, but also for your offer of continued support as well, because I can probably speak on behalf of several on the workshop today, and that it's only when we start to use the DosiGUI a little bit more and try to apply it that we may start to see where there are little areas that we could do with a little extra help with. And so that offer of asking questions in the future is really very much appreciated. So thank you for that. And then just to those of you on the call, I would just like to say thanks for joining, and I hope you found it as useful as I have. And please do keep in touch as you start to use the tools, because I'm sure that we can all learn from each other in terms of how we can apply it. And certainly that question around stickiness is quite key. And as you've already said, Artie, I think in terms of continuing the conversation on that one, it's going to be particularly important, because it clearly does result in quite big differences. And I think perhaps that's something that we've not really considered very much previously. So how to handle that moving forward, I think is going to be an interesting discussion to be had. So thanks to you. Thanks to you all for participation. But as I say, thanks especially to Artie, Pietro, Emez, and also Ilaria for support today. So I will hand over to yourself, Artie, to close. So I'm not sure if there are additional questions before we finish.
It doesn't look like it, but do feel free to send us an email if you do have further questions. So yeah, with that, thank you all of you for attending. I mean, we really appreciated the number of registrations that we had, and it's very exciting to go forward with this and facilitate everybody's use of this type of tool and quantification really of effective dose, which I think is very, very important for nanomaterials. Okay, so we'll say goodbye to everybody, and thank you very much for attending.
Thank you very much.
And thank you, Nicolina, for orchestrating all this.